Recording is now on, so we're back for the second half of the first day of fall 2020 4707. And we now have a Discord server. Check it out on the syllabus. And yes, please do start organizing some study sessions. You got that first homework assignment up there, go to it. Start reading the book and getting together and talking about it. And when you have really good questions, you don't want to be sending me questions just immediately when you get stumped on something, but if a whole group of you are having trouble and really think there's something difficult, send me a question by email. I'm not going to try to follow the Discord server all the time. I'm mostly going to let you folks use that. Okay. So here we were looking at our first counting principle, this product principle. We're trying to count the size of some set, capital A. And if we're so lucky that choosing elements of A can be done sequentially and you have a fixed number of choices at each step in the sequence, D1 choices, then D2 choices, and then DR choices to uniquely pick or define an element of A, that means the cardinality of A is the product, D1, D2 up to DR. And we did our first example, which is, that looks a little funny, subsets of an element set, and we want to understand why do there seem to be 2 to the n of them? And one way is to use this principle where you pick a subset S of the numbers 1 through n by first saying, yes or no, is 1 in there? Yes or no, is 2 in there? Yes or no, and so on, is n in there? And at each one of those yes or no stages, you had 2 choices, yes or no. So you take the product 2 times 2 times 2 times 2. Easy example, but before I go on to, some a little more interesting ones. Any questions? And other course structure questions that have come up. I caught some privately in the chat, but okay. So let's do our next example is pretty similar to Gotta get my desk set up here, right? How many ways are there if I've got n different posts, wooden posts that I want to paint, and I've got k different colors, so k cans of colors? How many ways could I just choose to arbitrarily paint them any of the k colors, those n posts? So let me label the posts, 1 through n. How many ways to paint n posts labeled 1, 2, up through n? So let me imagine picturing them. That's post number 1, post number 2, post number 3. Sorry, they kind of look like gravestones here. Whoa. Post number n. And I've got some different colors. Oh my gosh, look at these beautiful colors that I have. Like there's a pink, yeah. Here's an orange. Got some more colors here. Green, yeah. With k choices of colors. And there's no rules about how many times I use each color. Any color can be used on any post. I don't care. Any thoughts on this one? K to the n. Oh yeah, that's a good thought. So William, I agree. And so William, do you want to unmute and tell us why it's k to the n?
Sure. So for every single you have the same decision. You have k options of what color to pick, and then you just iterate that or whatever n times, and that's k to the n.
Yeah, again, it's one of these situations where it's pretty clear you could do it sequentially. You just, like, we already numbered the posts. Yeah, so D1 choices for first post, and that D1 is K, and then D2 is K choices for second, and so on. Dn is K for the nth, right? So the A is the number of K colorings, let me call it, of posts. Oh, sorry. A is the set of K colorings, not the number.
I mean, it could be K plus 1 to the N if you can leave them unpainted.
Sorry, why did you say K plus 1? I missed it.
If you leave them unpainted,
Yeah, I'm not allowing you to leave them unpainted. This is like Tom Sawyer, you got to paint the posts. Okay, N colorings of K colorings of N posts, that are labeled 1 through N. And we decided that the size of a cardinality is D1, D2. It's again this product principle, and it's K times K times K is K to the N. Answer. Everybody agree? Not much harder than our previous problem. In fact, you could even think of our previous problem with the subsets. You could think of like, oh, there's N posts, and I'm picking which ones do I like. I'm picking a subset of the posts that I like. And the question is number 1 a post that I like or dislike? Is number 2 a post that I like or dislike? It's like you're painting it with 2 colors, the like color or the dislike color. You're picking a subset of the posts that you like, and it's 2 to the N. Sound okay? All right. Let's do something that's getting a little more fancy. Okay, not real fancy. All right, we walk into one of my used to be favorite ice cream parlors. Back when I was a kid, there were limited number of ice cream parlors that had a lot of flavors, but one of them was Baskin Robbins. They had 31 flavors of ice cream. And the question is, suppose I ask you, oh, what's your first, second, and third favorite flavor of ice cream? All right, and me being boring, I'll say vanilla, chocolate, and strawberry. Now, that's really boring because like Baskin Robbins, they had 31 exotic flavors besides, vanilla, chocolate, and strawberry, but that would be one way that you could answer. 34 cubed. Okay, we'll write that down as a possibility, but I don't think that's it. All right, hold on. So how many ways to pick your first, second, and third favorite ice cream flavors from the 31 flavors offered by Baskin Robbins. By the way, you can look this up. We got more answers. Good. They used to call them their 30 wonderful flavors, Baskin Robbins. And by the way, you're not allowed to say, for example, I love coffee, and they usually had like a coffee flavor, but you're not allowed to say coffee, coffee, coffee. I really want, 3 different things to be in the list. And by the way, strawberry, chocolate, vanilla is different than vanilla, chocolate, strawberry, right? I'm really saying, first favorite, second favorite, third favorite. Yeah, so we're seeing some answers like 31 factorial divided by 31 minus 3 factorial. Yeah, I think that's right. Oh, okay, Matthew, right, corrected your answer to 31 times 30 times 20. Yes, let's take this to the next page. We got some correct answers, and let's see why we think these are correct. I like this 31 times 30 times 29. So yeah, Matthew, do you want to explain why you think it's that? You can unmute.
Wait, first of all, is it right?
It is right, yes.
Okay, good.
That is right.
So first off, your first choice, you have 31 choices for your first choice.
Okay, first choice, first favorite ice cream flavor choice.
Yeah, and since there are no repeats, your second choice is limited to 30 different flavors, only 30.
Right.
And then your third choice follows the same logic, so 29.
Yeah. Right, the point is no repeats there was the crucial thing. Everybody see why that is? Okay. Questions? Oh yeah, and people are writing some other ways of writing this, some other standard notations. Yeah, I'll probably avoid using some of these other standard notations like 31p3, for example, like on some kinds of scientific calculators. That's what this thing would be, is you would hit the button for 31p3 or npk, where n is 31. At any rate, let's actually now phrase that general question. So more generally, right, this is just an instance of this problem, which is how many ways to choose an ordered list of k elements from a set of n distinct choices. Ordered list of k distinct elements. Elements from n choices. So just to be clear, in that previous thing above, we were talking about k was 3. I wanted you to pick 3 first, second, and third favorite ice cream flavors, and then n was the number of flavors. It was 31. Everybody see what I'm notationally, what's going on there? And yes, right. So Theo and Nathaniel agree that it's going to be the formula that we're about to write down. But so let's write it down using product principle, and then we'll see that it's the same as the formula that they're writing down with factorials in the chat. Okay. So again, there's a D1, a D2, and a sequential process here by which we could choose those k things, our first favorite from the list, second favorite, down to our kth favorite. That's what I mean by an ordered list. We know which one was first favorite, second favorite, and so on. We know the order. And that first D1 is, well, we had the n flavors, or the n choices from the list, so n. D2, though, is n minus 1, because we're not allowed to repeat our first favorite from the list. And then D3 is n minus 2. And what's dk going to equal? Anybody see?
Donkey Kong 1.
No.
Well, 1.
No, dk is not going to be 1.
Oh, wait, it's not 1. It's not 1. Whoops, whoops. It's going to be n minus k.
Almost. Not quite.
Wait,
because,
n minus k. Wait.
Yeah.
N minus k plus 1.
Right. This thing is n minus 0. This one's n minus 1. This one's n minus 2. So that thing is going to be n minus, and it's almost k, but it's n minus k minus 1. Yeah. So that's our answer is this product. And maybe I'll write it with some, just to put in some parentheses to multiply those things. So there's a multiplication symbols. And that is actually the same thing as what some people have been writing in the chat. You know, there are many ways to write this. This is actually n factorial divided by n minus k factorial. Okay, so first of all, recall, what's n factorial? That's n times n minus 1 times n minus 2 if we went all the way down to 1, right? If we didn't stop at n minus k minus 1. So this is n minus 1, n minus 2, 3, 2, 1. Okay? And I'm going to let you think about it. Why is it that this thing, right, it's got too many terms, but this one exactly cancels out the terms that we don't see in that product? All right, so think about this. This is a good one for you to ponder a little bit. Why is that thing that I wrote up there as the answer the same as this expression? So this was the correct answer here. And this is another way of writing it. Everybody okay? Questions? Before we move on to more examples, we're going to do some more examples of this. Okay, good. This one now is not bad. Let's try. How many rearrangements are there of this word or the letters in the word snake? And I mean nonsense rearrangements. They don't have to make a word in any language. And SNAKE is one of the rearrangements. That one is allowed. I don't insist that you actually move things. 5 factorial. Yep, this is true. Okay, and yeah, so this one is simple enough given what we've already seen. So let's just explain why this is. So it's going to be 5 times 4 times 3 times 2 times 1, and that is 5 factorial, right? We saw that was the definition of factorials. When you take a number n factorial, you go all the way down to 3 times 2 times 1 from n and n minus 1. Next problem, sneak. Oh, it's a good suggestion. We will get there. Yeah, good suggestions for ones we could do next, but yeah, maybe not quite next. We will get there though. All right, so again, this is because when you're doing the rearrangement, right, you first pick the first letter, could be anybody, could be the K. And then you pick the second letter, could be anybody, except it can't be the K. Maybe it's going to be the A. And then you pick the third letter, and maybe it's, it could be anybody except the K and the A. Maybe it's the E. And then you pick the fourth letter, maybe that's going to be finally the N, and then maybe you have no choice, one choice for the last letter. So everybody see how this is, again, one of these, it's an instance of the previous problem, really, because what we had to do was we had to take from the set of the 5 letters that were all distinct. N was 5, but K was also 5. We were asking ourselves to pick our first favorite letter to put at the beginning of the word, our second favorite letter to put at second place in the word, third favorite, fourth favorite, really down to the whole thing, fifth favorite. In other words, we were asking ourselves to list them in order of how much we like the letters, and that's another way of thinking about such a rearrangement. Everybody okay with this? All right. And, it's more generally, this is called permutations. How many permutations? That's what these things are called when you order the elements, n distinct elements. How many permutations of n objects, like the numbers 1 through n, and it's n factorial. Oop, not m factorial, n factorial. So n minus 1, n minus 2, and so on. So those factorials are also answering one of our questions. And we think of it as, again, being one of these products in which, notice at that last stage, right? When you get to the nth stage, you have no choice. When I've already used the K, the A, the E, and the N, there's only one letter left. D1 is 1. There's one choice at the last stage, and that's where that 1 comes from. Everybody okay? All right, so those are some correct answers to these problems. And this is this general story there. Okay, let's try one that's a little more fun. Any questions about these previous examples of product principle? Sorry that I'm doing so many with the product principle, but really this is the one that you want to try to reduce all other problems, is get them back to the product principle by other counting techniques that reduce it to it. So we want to get good at this one. Questions? Okay. Last one in product principle. Is it the last one? Yes, it is. We're at summer camp, and I have an even number of campers, 2N of them, and we're about to go swimming. And this is not the time of the pandemic, you know, where people are afraid to touch each other. You know, this is like, we need to pair off as buddies. Like, I'm going to make them hold up their buddy's hand and say, who's your buddy when you go swimming for safety? Just so you're always watching your swim buddy. The question is, with these 2N different campers, there's an even number of them, 2 times N, and they have these very unimaginative names. The children, these campers, are named 1, 2, 3, 4, up to 2N. How many ways can I pair them off to do their swimming? So pair them off into swim buddies. And I think we should experiment a little bit. Let's just steal this question here, copy it over. What's my clue that we should be experimenting? Okay, yeah. Hold that thought, Thea. Let's do some experimentation first. Let's just do it. I'm gonna say for like N is 1. Let's look at the buddy pairings and count them. There's only two kids, 2 campers. Wow, that was kind of messy. I'm gonna put an edge between them when they're paired, 1 and 2. And so there's the number of possible pairings is only 1. That's a 1, by the way. Sorry, my 1s look a little funny. That's a 1. It's not a 7. Okay, that wasn't so interesting. Let's take N equals 2. So it's not that there's 2 children when N equals 2. Now there's 2 times 2. There's 4 children. So I got these children, 1, 2, 3, 4. And let's see how many ways we can pair them up. I'm going to draw edges between them when they're paired. Like, I could pair up 1 and 2, and then 3 and 4 are stuck. They're going to be paired together. And I could pair up 1 and 3, and then 2 and 4 are going to be stuck together. Any others?
One and 4.
4.
Yeah, I'm not sure why I wasn't doing that. It's not like I care about whether 1 and 4 dislike each other. No, I'm ignoring that. You're stuck with each other, 1 and 4. And then 2 and 3, you're stuck with each other. Any more?
Nope.
Nope. Yeah, you can see that's it. Okay, 6 kids, here we go. Are we going to do all of these? I don't know. I mean, let's start doing some of these. I don't think we're going to want to write them all. This one actually starts to get big. Yeah, I think you just said the right number.
Oh. Is it? No, that's 16 minus 1. So is it like 2? Okay, and then is the next? Wait, okay, never mind. I'll think about this some more.
Let's do these. Okay, maybe 1 goes with 2 and 3 goes with 4 and 5 goes with 6. Okay, maybe 1 goes to 2 and 3 goes with 5 and 4 goes with 6. Maybe 1 goes with 2 and 3 goes with 6 and 4 goes with 5. I don't know. Maybe 1 goes with 6 and 2 goes with 5 and 3 goes with. There's a whole bunch of them, and you know, if you actually do this next case, you'll find that there are 15. That's not a 75. That's a 15. Okay. And if you factor this, you're going to see, this is, 5 times 3. And yeah, somebody already wrote, there was something in there that was sounding promising. Product of all the odds up to 2n minus 1. Okay, William, that sounds reasonable, because if you factor this, right, this is 5 times 3. This one was just a 3, and this one was just a 1. You can rewrite this as 1, 3 times 1, 5 times 3 times 1. And indeed, if you, now at this stage, maybe you're actually good at getting a computer to list things for you. Maybe you could write a program that lists them all, because you probably don't want to do it by hand. For 4, you're going to find that indeed you get, yes, whatever the next thing is, 105, I think, is 7 times 5 times 3 times 1. And it is the product of all the odds up to, yeah, what you wrote, 2n minus 1. Okay, so let me steal the question again.
Okay, I think I have a thing. I think it's 2n factorial over n factorial, and that all is over 2 to the n.
I think that'll work.
So I
Yeah.
think-
First, let's see whether we believe why this first way we wrote it is the 2n minus 1, 2n minus 3. So that's what we're going to say. Is the answer is if A is this number, the set of all pairings. All right, so then we're saying this is going to be 2n minus 1 times 2n minus 3. So 2n minus 1 is an odd number. 2n minus 3 is an odd number. And you go all the way down, and you're going to be writing a total of, yeah, n odd numbers. And somebody wrote a notation in the chat, Mark, yeah, this is sometimes called 2n double. You're writing 2n minus 1 double factorial. To be honest with you, I can't even quite remember whether they would write it as 2n double factorial. I don't know. You know what, Mark? I'm going to avoid using that notation anyway. So there is some kind of a double factorial notation for it, but it's not important that we memorize it. First, let's make sure we understand this. So how do I think about this in terms of a D1, a D2, and so on? I guess this guy is going to be Dn minus 2. No, not quite. The 5 is going to be Dn minus 2. And then there's going to be a Dn minus 1 and a Dn. So there's, the 7 would be like Dn minus 3. Yeah, so let's who was saying, where the heck was this? I'm trying to find where somebody was saying the product of odd numbers. Oh, I lost it. Whoever was saying the product of odd numbers up to 2n minus 1. Can you explain this in terms of product principle?
Yeah, so when you're making your first group, yeah, so D1 is equal to 2n. Yeah, I mean, you have it right there.
Yeah, why? So what is this? What's going on? What's this
So
choice here for the 2n minus 1?
Okay, so when you're forming your first group, you have one person who you pull aside, and like, who do you want to buddy with? And you have 2n minus 1 choices.
Wait, how did I pick that one person?
It doesn't matter because it's just because the ordering of who you pair first doesn't matter because it can just be any person that's in a pair.
Yeah, so this is an issue. Like you've got these n people lined up. Let me do this maybe for n is 6. And so when you're thinking about how to do this sequentially, you have to think about it. Can this really be done by a set of sequential choices? Yeah, Kevin, why don't you try to explain it to me?
Oh, wait.
Yeah. Hold on, William. I want to hear Kevin's explanation of this. No, Theo's trying to explain it. Kevin doesn't have a mic. Okay, Theo, you can try to explain it.
Okay, so no matter what, person one has to pair up with somebody, right?
That's right. So you take person number one. You have to choose them at the very beginning, but maybe it's alphabetical. Person one perhaps has the first name in the alphabet. And you can ask,
Yeah, so you can choose one, and then they pair up with a random person. There are 11 ways for you to do that, because person one can pair up with anywhere from 2 to 12. So then you can just choose the next person, and then they can pair up with any of 9 people.
Yeah, who's the next person? What did you mean by the next?
Well, the next person after person number 1 would be person number 2, but if person number 1 paired up with person number 2, then that would be person 3.
Okay, so that's an important point. You really can do this sequentially, and it doesn't matter what happened at that first stage. When the person who was alphabetically first, or whatever, how you chose it, they might have made, among their 2n-1 choices, and that's this 11 choices in this case, they might have picked the alphabetically next person, but then it doesn't matter. You pick who is the first alphabetically who has not yet been paired. So that would have to be, I don't know, number 2 in this case, or number 3 in this case. And they now have how many choices?
9. Which means that the next one has to have 7. The one after that has 5, and so on.
Yep. Does everybody understand? Why it doesn't matter how the first 2 choices went. You now remove those buddy pairs, go send them in the water, and everybody else is still on the beach. And you find the alphabetically first person left, In both cases, it happened to be number 4. Oh, no. What did I do? Sorry, no, in this case, yeah. In this case, it was 4. In this case, it was, excuse me. In this case, it was 3. And in this case, it was 4. The alphabetically first person left on the beach after you did 2 pairings. And they will always have, right, in this case, it's 2n-5 choices left because 2n-5, because there's 4 people in the water, they can't pick themselves, and so there's 2n-5. Okay, so let me emphasize this. That was a 2n-5. That was a 2n-5. At the first stage, that first person choosing, they had 2n-1. At the second stage, these people had 2n-3. Right? Why was it at the second stage they had 2n-3? It's because 2 people are in the water. They are the alphabetically first. They can't pick themselves. That means 3 people have been eliminated. There's 2n-3 people on land waiting to be picked by them. Okay, we got some questions in the chat. What if you have an odd number? Then we can't do the buddy pairing. Swimming is off because somebody's going to be unpaired. Nobody gets to swim. It's unfair, but that's the way it is. Right, we don't ask this question then. Triple group, yeah, that's a different problem. Someone pairs up with the teacher. No, thank you. Okay, so everybody good with these product problems that we've been doing? Okay. Should we learn another counting principle? Yes, we should, of course. I know the answer to that question. All right. So let's do our next counting principle if there are no other questions about this stuff. Oh, sorry. And I forgot to say what another way to write this formula. Here, this is an exercise for you. This is actually equal to, oh yeah, let's make this blue. Yes, this is 2n factorial divided by n factorial and a 2 to the n in the denominator. So again, this is think about this. Why it is that cancels down to this formula. That is a valid formula. I think a couple of people wrote in the chat. Yeah. Good. Questions before we move on to the next page, next counting principle? Okay. Sum principle. This one you might have thought, shouldn't I have done this one first? This one seems even easier. Sum principle is really simple. It says, when do you add when you're counting? If a set that I'm trying to count, A, is a disjoint union. This is going to come up so much, disjoint union, A1, disjoint union, A2. I'm going to introduce this notation. So this is what I call a disjoint union, and it just means not only is A the union of A1 and A2, but also there's no intersection. A1 intersect A2 is equal to the empty set. We're getting our set notations reviewed here. If these notations don't make sense to you, then you should talk to me in the office hour and we can review some notation there. All right, if we're in that situation where A is the disjoint union of A1 and A2, then guess what? The size of A is the size of A1 plus the size of A2. It's the sum. Not a big surprise there. I can't remember what color I made this last time. Was it red? Oh, I missed it. Anyway, it's not that hard. And more generally, if you've got your set A broken up into several pieces, say it's A1, disjoint union A2, disjoint union AR, then the cardinality of A is the sum of the cardinalities. And here I really mean pairwise. You know, each of these A1 through AR are disjoint from each other pairwise. And what the heck, let's remind ourselves that we could always use a summation notation here in that setting. Okay. And let's do a quick example. We're only going to do one example of this today, but we will use it more in the future. So remember when we were rearranging the letters in snake? So the SN, the K, AK, and E. I want to ask you, how many of them have the S and the N next to each other, adjacent, anywhere? Any thoughts on how we might analyze this? Yeah, so Theo's saying we should look at the S and the N. They could look, it could be something like AKSNE. Could also look something like AKNSE. Those are both okay, for example. Yeah, so Adesh, you have a good idea there. Treat the S and N as a single unit and then multiply the final answer by 2 factorial. Right, and that's what David's saying. One can have an SN and an NS. Yeah, Mark, you're asking me whether SN or NS, either one is okay. I would allow that SN or NS adjacent. Oh, Theo's trying to do something probabilistic. That's a fun way to think about these things. But let me ask you this. How many are there like this where the SN are adjacent with the S before the N? Can anybody tell me how many are going to have a little, the way that Adesh was saying it? If we treat the S and N as a single unit and it's SN in that order, how many ways are there?
4 factorial.
Yeah. So,
And then you multiply that by the number of permutations of Sn, which is 2 factorial.
yeah. But I'm just going to think about it breaking up into these 2 sets. So there are 4 factorial of these, rearranging A, K, and let's just think about it like Adesh was saying, like SN is some kind of super letter, SN. SN. We wish we had that in the English alphabet. And then if we try to count these, where there's a super letter that's NS, NS, there are 4 factorial of these where you're rearranging A, K, Ns, and E.
Oh, and you can add them together?
Yeah, and we can add them together, right? Those are disjoint sets, right? I've taken my rearrangement set. That's my set A. There's the rearrangements, that are doing this. That's A1. And then there's the rearrangements of this. That's A2. And it's definitely broken up into a disjoint union of those 2 sets. Does everybody see that? Okay, so let me steal this. On the next page. So A1. So all such rearrangements is A. This one is those with SN as a letter, and those with A2 is those with NS. Let me write this as a super letter. And I'm just making up that word super letter. I just mean this like combined letter. Okay, so.
This reminds me of a video I saw on Fancy Palindromes by Carrie something. I forgot his last, or I'll link it later.
I don't know that one. Wait, what's 4 factorial is 24. All right, so everybody believe that? That was just using this sum principle in a relatively simple way. All right, plan now. I went over by 5 minutes. Sorry, it happens. We were kind of dithering around at the beginning of the class, talking about syllabus for a while. I'm going to stop the recording. Recording is going off now. Any questions that anybody wants on the recording before I turn it off? Okay.